In 1801, the English scientist by the name of Thomas Young did an interesting experiment that showed once and for all that light is definitely a wave. Here's what Young's double slit experiment is. He took a sheet, a sheet that had two slits in it, and he shined the light of the sun through those slits. And then he had a viewing screen on the back side. The question is, what was on the viewing screen after the sun shone through it? Well, one would think that you would just see two little slits of light from the sun shining through, and you've got two bands of light from the sun shining through those lights. Excuse me, from the light shining through those slits. But what Thomas Young actually saw was a series of bright bands of light. Not at all just a pattern of the two slits. Very, very different. Now, using just regular logic, this makes no sense at all. But when you go back to Huygens' principle, this actually makes a lot of sense. Here's what's happening. You have the two slits inside of your barrier, and each slit is the source of new wavelets. And as these wavelets pass from the slits towards the view screen, the waves get larger and start overlapping on top of each other and interfering with each other. Remember back when we talked about interference, we had two different types of interference. We have the regions where crests meet with crests, such as what we have here whenever lines pass on top of each other. And then you also have regions where troughs meet troughs. So those would be these spaces here. Now, these regions, since they are in phase with each other, the amplitudes add to each other and you end up with constructive interference. And so if we just drew a line that combined these, and there you have another one down here, then you get regions of constructive interference. Now, notice what's happening in between these lines that I just drew. Here you have a crest right on top of a trough. Crest on top of trough, crest on top of trough. Well, what happens when you have two waves that are out of phase with each other, meaning you have a crest meeting a trough? Well, there you get destructive interference and you end up with dark bands. So what you would see then is you would see a bright band of light on the wall wherever you have constructive interference, and then a whole bunch of nothing. So you get what a bright fringe, then you get a dark fringe, followed by another bright fringe, followed by another dark fringe, and another bright fringe, and it goes on and on and on until the intensity just gets so weak that our eyes can't even see it. So if light is a wave, this is what you would see. But if light were just particles, you would just see the two bright bands from the slits. Thomas Young did the experiment. This is what he saw, proving once and for all that sure enough, light really is a wave. Here's another look at what's happening. You have the two slits. Light passes through. The light originally is in phase with each other. The individual light waves are in phase with each other. A point right in the middle is equidistant from both slits, which means that both waves have to pass the same distance, which means they're still in phase with each other when they reach that central point. Since they're in phase with each other, you get constructive interference. At some angle theta from that central point, the second wave has further to go, but how much more it has to go would be some multiple of its wavelength. So basically, at this point up here, this wave down here had to pass one extra wavelength, or maybe 2 extra wavelengths. Either way, by the time it reaches, you're still in phase and you get constructive interference. But here in this case, when you get half of that distance, at this point here, you get destructive interference. Why? Because now, at this particular angle, this wave has to travel an extra distance more than the other wave, but it only has to travel an extra half a wavelength to reach the wall, which means while the top wave may be at a crest, the second wave is now at a trough, or vice versa, meaning they're out of phase with each other. You get destructive interference. And that's what causes the dark places in between each of the light fringes. So geometrically, how can we describe this? Well, Thomas Young went through and found this calculation and found that if you take the distance between the two slits, so there's your obstruction with your two slits, that distance right there is D. And then multiply that by the sine of theta, then that's going to equal the m number times the wavelength of the light. Now here's what we mean by the m number. Let me draw it up here. So you get light that passes through these two double slits. You end up with a bright fringe and then a series of fringes on either side. The m number describes which fringe you are looking at. The one in the very center is 0. The fringe on either side is m equals 1. The fringe just beyond that would be m equals 2. And the fringe just beyond that would be m equals 3. And so on. So we find that d sine theta equals m lambda. M is just any whole number, 0, 1, 2, 3, whatever whole number you're looking for. That's the fringe number. And this is how you find the location of all the constructive interference spots. In other words, where are all of your bright fringes located? Well, what if you want the destructive interference areas or the dark fringes? Well, there you just go halfway in between M0 and M1, and so we need to add a half. So this would be 1/2, halfway between 0 and 1, 1.5, 2.5, so on. So we just take our m number, whatever the m number is, and add half to it. And this equation will then give us the locations of all of our dark fringes. Now, between the maxima and the minima, you have amplitudes that are always changing. The central fringe is always going to be the brightest. And then, of course, your amplitude drops to 0 whenever you reach areas of destructive interference. Those would be your minima. And then you reach your next maxima, your m equals 1 point, and you see that its amplitude is actually decreased a little bit. And that just gets weaker and weaker from there. So the amplitude of your maxima points actually decreases as you go further out. One last thing about Young's double slit experiment that's really interesting, and that is that, remember, our equation is d sine theta is equal to m lambda, meaning it depends on the wavelength. How far your light diffracts depends on the wavelength. Now for the m equals 0 fringe, the very central fringe, that doesn't matter. And so all of your light is going to reach that central fringe and combine at that one point, creating a band of white light. But because violet light has a shorter wavelength, it's going to diffract less. So as you have a smaller wavelength, you're going to have a smaller angle, smaller sine theta, which means smaller angle theta. So your violet light with a shorter wavelength is going to diffract less, where green light has a longer wavelength, so it diffracts more, yellow more still, red the most. And so you end up with a spectrum of colors instead of just a single white band. Now, as soon as this video is done, which is happening in just a couple seconds, I will have a subsequent video on Falcon Online where you will be able to see a cool experiment that someone did to show people in the public exactly what you would see. And when you see this experiment and you see what they, I'm not making sense. Let me explain this again. He takes a double slit experiment out, shines the sun through the double slit, and allows people to actually see this diffraction pattern that you see here on the screen right now. It's pretty cool to see, but one thing I wanted to point out is you are going to see this band of colors as it diffracts. Since each color has a different wavelength, it's going to diffract at different angles.